Hey students, I thought I'd try another solution. I got a question. It really is kind of the same question as 35. That's why I thought I would do these together. Somebody asked about 33, and I just did the video on that one. Maybe you watched it. And now looks at 35. And there is a small difference between these two problems. But one thing that was hopefully interpreted well by you guys was that this equation d sine theta equals to m lambda, where you get the maximums, whether or not you have 2 slits or 3 slits, or in this case 10 narrow slits, the same result occurs. Now, there are some things that are different. For example, the minimums for the double slit, d sine theta equals to an integer and a half, where the minimums are for the double slit, being right between the two, does not work when you have 10 slits. And in fact, it gets very complicated, and we didn't even talk about what the diffraction pattern would look like when you had 10 slits in totality. We only looked at where the maximums are. And so that's what I'm going to take advantage of and say 35 is a lot like 33 in the sense that this would give me the places where you have your maximums. Of course, another thing different between 33 and 35 is 33 has 2 different colors coming into our double slit. Here, we just have a single color coming in. So 10 narrow slits are equally spaced, and they are 1/4 of a millimeter apart, and they're illuminated with yellow light of wavelength 580 nanometers. What is the angular position of the third and the fourth? So if you rearrange this equation and say sine theta equals to m lambda over d, and you use radians and what we call the small angle approximation, you could say then this is the equation to get the angular position. And so if you had these 10 slits, 1, 2, 3, 4, 5, I'll just pretend there's 10 there, and then you have this straight through, you'll have your first maximum, so m equal 1, your center maximum, m equal to 0, and then m equal 2 and m equal 3. And so we're looking at m equal 3 and m equal 4. So we're looking at where is the angle for this one, call it theta 3, and what is the angle of this one, call it theta 4. And so mathematically I would do this. Theta 3 equals 3 times the wavelength, 580 nanometers, and divided by, whoops, I meant to put a D there, divided by D, equally spaced at 1/4 of a millimeter. And then, of course, 4 would look a lot like this. It would just have a 4 for the higher order. All right, so grabbing my calculator here, this would be 3 times 580 nanometers divided by 1/4 of a millimeter, and in terms of radians, 0.00696. And if we do a re-enter here and change our 3 to a 4, we're looking at 0.00928. And so that's the 2 angles. And so that's this first part. A, what are the angular positions of the third and fourth? And so then when it goes on to say B, so maybe I should put a little A here. B, what is the separation of these maximums on the screen that is 2 meters away? We could do like we did back in 33, and I'll just kind of review some geometry that's easy to forget. But when you have an angle and an arc length, the arc length S is the angle times the radius, coming from the definition of the angle in radians. This is how the ancient Greek defined the angle. They said take the arc length and divide it by the radius, and that'll be your angle. And so they got an angle in what today we call radians, as opposed to chopping it up into numbers that are highly divisible like the Egyptians and Babylonians, and that's how they got their 360. So we've got both systems, the 360 degrees, and we got the radians. And in this case, I think it would be better to use radians because of this step right here, because they want me to find it on the screen. And we can kind of come over here and say, well, this screen isn't quite an arc, but it's pretty close by the time you realize that this distance here is 2 meters, but these distances are only 1/4 of a millimeter. And so this is actually really tiny, and this is really far. And so we can say that, this screen over here is essentially part of a arc, or the arc is so big it's kind of flat. See, and where that is helpful then is we can then say, all right, my position of the third bright one would be this angle times the 2 meters. So coming up here and grabbing that angle and multiplying it by 2 meters, I would say it's 0.0139 meters. I guess if you want, you could call it 13.9 millimeters. So this is why I was saying it's kind of a short distance. And so you can just go a short distance down, roughly about 14 millimeters, and you'll get to the third bright fringe of this multiple slit, 10 narrow slits. And then S4 is that same logic, taking that angle. So let me take that 0.00928 and multiplying it by my 2 meters. And we're looking at 0.018, and I guess I'll round that to a 6 meters. Or you might say 18.6 millimeters. And of course, the question in B says, what is the separation? And so subtracting the two, you would have, what's the position of the fourth compared to the position of the third? So you would have this 13.9, this 18.6, and subtract them. And I guess I should have done big one first, but ignoring the negative here, this is 0.00464 meters, or 4.64 millimeters. And so there's the separation there. Okay. Hope that helps. Take care.